We have two-slit interference here. The slits are separated by a distance d, and the light passes through the slits and makes a pattern on the wall over here. There's some kind of a central maximum, and then there's a first minimum, and so on. Okay, so here's the center of the pattern. Probably made the pattern too big. But let's see, so the slits are separated by 0.30 millimeters. And the light from these slits is going to go over to the wall to the first minimum over here. Right? And it's going to make an angle theta. Right? Where theta is this distance y1 over L. Right? That's going to be that triangle that we're looking at. Now remember, this is not to scale. These slits are supposed to be very small and so forth. Really, the angle theta that we're measuring is the angle from the center to here. And you have to remember that these are parallel lines. They don't look parallel, but of course if the slits are really close together, they're parallel. Now, in this circumstance, we have the equation that the first dark fringe, the first minimum, is at a location of d sine theta is equal to y1. Sorry, d sine theta is equal to lambda over 2, half a wavelength, right? We want the path difference for the first minimum to be half a wavelength. That means that this distance right here, d sine theta, is half a wavelength. Now d sine theta is dy1 over L. So if I solve that for lambda, part A it's asking for lambda. If I solve for lambda, that's 2 dy over L, which is 2 times 0.3 millimeters. Oops, sorry. Let's start over. 2 times oh my gosh, I can't do this. 2 times 0.3 millimeters times L. Oh, I'm sorry, times Y. That's 1.3 centimeters. Right? Notice that it says that the width of the central maximum is measured to be 2.6, right? This is 2.6. That whole thing is 2.6. So half of that is 1.3 centimeters, right? There's my centimeters. And then we divide by L. We're told that the wall is 12.5 meters away. Okay? So D was given, and Y1 we had to kind of do a little bit of figuring to get that correct. So when we get lambda there, we get 624 nanometers. 6.24 times 10 to the minus 7, but it works out to be 624 nanometers. Now, part B says if the wavelength of the light source is decreased, what will happen to the central maximum? Well, let's consider, let's solve for y here. Y is equal to lambda L over 2D. That's, again, still the position of the first minimum. So if L stays the same and D stays the same, and what happens is the wavelength is decreased, right? So the wavelength goes down. That means Y1 has to go down. Y1 is directly proportional to the wavelength. So if lambda decreases, then Y1 decreases. And that means that the central maximum narrows, gets thinner, right? Because if this goes down, then the central maximum is going to get cut. Okay, so there's your answer for part B.